All right, guys, we're going to continue our look at sequences here. We spent a lot of time talking about sequences in general and also arithmetic sequences we spent a couple days looking at. So it may be helpful just to review one last time what an arithmetic sequence is. And if you remember, an arithmetic sequence, right, is a sequence, okay, that changes by a constant that we called d, right? So an example of an arithmetic sequence is something like 2, 4, 6, 8, 10, 12, dot, dot, dot. In that case, it's increasing by 2, so we would say our d value was 2, is increasing, right, 2 each time. All right, so we spent a lot of time coming up with explicit and recursive formulas for that, for finding the next term in a sequence, and so on. I want to now look at some other types of sequences, because there are certainly other types of sequences we could have that are patterns that we can predict that aren't always just changing by the same amount. So let's take a look at problem number 1, problem number 2, and problem number 3, and see if you can figure out what they all have in common. I'll give you a second to think about it. Maybe hit pause. See if you can figure out what's common amongst all 3 of them. Okay, so if you look at number 1, it looks like to get the next term in 1, 2, 4, 8, 16, 32, 64, we are doubling all of them, right? We are doubling all of them. In problem 2, it looks like we are dividing them all by 2, or multiplying by 1/2, right? To go from 2 to 1, multiply by 1/2. To get from 1 to 1/2, multiply by 1/2. To get from 1/2 to 1/4, multiply by 1/2, and so on. Problem number 3, 3, 9, 27, 81, and so on. It looks like to get the next number, you take the previous number and multiply all of them by 3. 3 times 3 is 9. 9 times 3 is 27. 27 times 3 is 81. So it looks like if I'm trying to find a commonality amongst all these 3, that to find the next term, it all depends on multiplying the previous term by some number, and it's constant each time. All right, so if I were to really write this out and define it, I would just say maybe that the next term, right, in the sequence can be found by multiplying the previous term by the same constant. Now notice how that's different than arithmetic. We weren't multiplying the previous term when we were doing arithmetic, we were adding to the previous term. Here in these 3, we are multiplying the previous term by something. It's the same number each time, but we're still multiplying. So these are all examples, you can guess by the title of the worksheet here, that these are all examples of what we call geometric sequences. Okay, so to get from one term to the next in geometric sequences, you multiply the previous term by, not d in this case for difference, we're going to use the term r when we talk about geometric, r standing for ratio. Okay, so under arithmetic we had d, which stood for difference between them. When we talk about geometric sequences, those are going to be referred to as r, or what the ratio is. What are we multiplying each one by? So much like we did before, let's take a look at maybe some example sequences and see if they are geometric, or if they're arithmetic, or if they're something different. So if we look at something like a simple sequence a sub n equals 2 to the 2n, well, the first term would be a sub 1 equals 2, because 2 to the 1 is 2. A sub 2, 2 to the second would be 4. A sub 3, 2 to the third is 8. A sub 4, 2 to the fourth is 16. So it looks like, to go, if I'm looking at the sequence in numbers, 2, 4, 8, 16, all the numbers are being multiplied by 2. So this gives me confidence that this certainly is a geometric sequence. If we do a sub n equals n cubed, I get a sub 1 equals 1 cubed, or 1. A sub 2 equals 2 cubed, which is 8. A sub 3 equals 3 cubed, which is 27. All right, I can stop there, right? To go from 1 to 8 via multiplication, r would have to be 8. However, to get from 8 to 27, r would have to be, I don't know, some decimal, like 3 point something. So the r value would have to be something different. Right? I don't know exactly what it is, but it would be different. So that is certainly not an arithmetic sequence. So it looks like, if I'm doing some early analysis here, it looks like if the variable is in the exponent, it's a geometric. However, if it's in the base and the exponent's just a number, it's not geometric. So that would seem to me maybe the third one's geometric, but let's work it through just to confirm. The first term, a sub 1 equals 2 to the 1 plus 1 is 3. A sub 2, 2 to the 2 is 4 plus 1 is 5. A sub 3 equals 2 to the 3, which is 8, which is 9. Ooh, interesting. The d value, what I would take to multiply 3 to get 5 and 5 to get 9 is a different number. That is not the same. So it looks like this is not geometric. And really what's screwing it up, why is this not geometric whereas the first one was? It's that 1 there. And that 1 really screws it up. So when we have these geometric sequences, you can't have a number to the n power and then add or subtract something. That's going to screw up the geometric sequence. So that one is not geometric. But what if we were to take that number to the n power and multiply it? Would that make a difference, or is it still not going to be geometric? Well, let's try it. A sub 1 equals 12. Right? 3 to the 1 is 3. 4 times 3 is 12. 3 to the second power is 9. 9 times 4 is 36. A sub 3. 3 to the 3 is 27. Times 4 is 108. To go from 12 to 36, r would have to be 3. To go from 36 to 108, r would have to be 3. Ooh. So it looks like that was okay as well. So we have 2 geometric sequences and 2 ones that were not. It looks like if I have a number multiplying that number to the n power, that works. But if it's being added, it doesn't. Okay, so those are some geometrics and some ones that are not. So much like arithmetic, we had a general formula. And let's maybe just rewrite this out again. So for arithmetic, just so you can see the differences side by side, right? For my explicit formula, it was a sub n equals a sub k plus n minus k times d. Okay, that was our general form for arithmetic, and we kind of know what all those pieces mean. For geometric, it's sort of similar, a little bit different. It's a sub n equals a sub k. So far it looks identical, but instead of plus, look what we saw up here. When it's a number, we're going to do times, okay? Instead of d, it's r. And then notice how all of these that were geometric had variables in the exponent. I'm going to put n minus k in my exponent. So that's your general form, okay, for geometric. This is explicit, okay? Don't worry, we're not going to do recursive for geometric. We're just going to stick with explicit. So only one formula to worry about with geometric. For arithmetic, we'll still have to worry about 2, okay? But for geometric, we'll only stick with the explicit formulas. All right, so this is going to kind of follow a similar pattern to arithmetic. So we're going to be able to fly through some of these problems fairly quickly. So example 1, find the 12th term of the sequence 5, 15, 45, etc. So much like we did before, we are going to have to find the r value first. We had to find the d value when we did arithmetic. Here we're going to have to find r value, so we need to look at this and say, all right, what do we need to multiply 5 by to get 15? What do I need to multiply 15 by to get 45? Hopefully you'll be able to see from here that in this case r is equal to 3. So if r is equal to 3, let me use my general formula. A sub n equals a sub k, which is any number we choose. So let's choose 5 since it's the smallest, times my r value, which is 3, to the n minus k. So it's n is your variable, minus, again, k is the place of that term. 5, what was that term? It was the first term. So it's going to be minus 1. So that's your explicit formula. And again, the nice thing about explicit formulas is that once you have the formula, you can use that formula to find any term in the sequence. So if I want to find the 12th term, I do a sub 12 equals 5 times 3. And let me actually do this just so I can really highlight things. If I want to find a sub 12, I need to plug in 12 in both spots. So you can see in red where it's 12, a sub 12 equals 5 times 3 to the 12 minus 1. If you do that out in the calculator, make sure you raise 3 to the 11th power first before you multiply by 5. If you do that, you get 8, 8, 5, 7, 3, 5. Okay. Example 2 is a little bit trickier. Okay. So the fourth term of a geometric sequence. Okay, fourth term of a geometric sequence is 125, and the 10th term is 125 over 64. Find the 14th term in the sequence. All right, so in order to do this, notice we don't have the R value. So what we're actually going to do is we're going to use the explicit formula to find the R value. So again, remember my explicit formula was a sub n equals a sub k times R to the n minus k. If I were to fill in a formula here, I could say a sub n equals 125 times R to the n minus 4. I could get that far. I don't know the R value yet. So what I could do from here to find the R value is use an example term to plug in to solve for R. So the example term I have is 125 over 64. So remember that's the 10th term. So I could say 125 over 64 equals 125 times R, okay, times n, which again, this is the 10th term. So I'll plug in 10 for n, right? It's still minus 4. Notice now my only variable is R. So it's kind of like when you're doing a slope-intercept form. Let's say you had y equals 2x plus b, and you wanted to solve for b, and you knew a point was 2, 3. You plugged in 2 for x and y to solve for b. We're plugging in an example term in the sequence to solve for r. So it's very similar to that process. So let's kind of work through this process. If I divide both sides by 125, I'm left with 1/64 equals r to the 10 minus 4, which is 6. Okay. Okay. I then need to take the 6th root of both sides. So that means I'm just going to switch r to the left side. I get 6th root of 1 over the 6th root of 64. 6th root of 1 is 1. For the 6th root of 64, you have to say what multiplied by itself 6 times gives me 64. Turns out that number is 2. Okay, so that is our R value. Okay, it is our R value. So to find the 14th term in the sequence, let me write out my formula. 125, I now know my R value is 1/2 times n minus 4. That's your explicit formula. Right? And now to find the 14th term, we're going to plug in 14. You'll need a calculator for this one. Again, make sure you raise 1/2 to the 14 minus 10, or the 4th power, before you multiply by 1. Oh, not by 10. I screwed that up. Should be times minus 4. Right? 14 minus 4. If you do that out on the calculator, it's going to give you 0.122. You can round to 3 decimals there. That's a tough one. Okay, that's a tough one. Again, to review, okay, let's review our steps real quickly. Right, we first set up the formula with at least what we knew. Right, we knew 125 was a sample term, and I knew k was 4 because that sample term was the 4th term. I then used a sample term in the sequence, another one, the 10th term, which is 125 over 64, to fill in to fill in a couple variables to help me solve for R, so I could create an explicit formula. And again, it was similar to that process of being given an equation of a line and you needed to solve maybe for b, you would plug in 3 for y and 2 for x to solve for b. It's that similar idea, but now we're just solving for r. And then once we had r, it allowed me to find the explicit formula there, and then once I have the explicit formula, I can plug in 14. All right. Our example 3 is very similar to 1, and 4 is very similar to 2. So here's what I would suggest. I would hit pause on the video and try to work through 3 and 4 right now. And then once you've gotten those two, hit play and check to see if your answers match mine. All right, for 3, very similar to 1, I'm going to write out the explicit formula first. So a sub n equals 4, which is the first term, times the r value, which is 4, right? Oops. R value is 4, times 4 to the n minus 1. It's minus 1 because I'm using 4 here as my first term. You cannot combine that to 16 to the n minus 1. Do not do that. Find the 9th term. So now I just do a sub 9 equals 4 times 4 to the 9 minus 1. I really do this the long way. It's 4 times 4 to the 8th. Do 4 to the 8th and then multiply by 4. It is not 16 to the 8th. In this case, a sub 9 equals 262,144. All right, and for example 4, very similar to 2. I'm just going to write out the explicit sequence again, just so I have it handy, times r to the n minus k. I'm going to use the third term here, but you could use the other term. It really doesn't matter. We should get the same answer. So I know a sub n equals a sub k, which is 100, times r, which I do not know, minus 3. I don't know r. And now I'm going to use, in this case, the 5th term as my sample term to help solve for r. So I'm going to say 25 equals 100 times r to the 5 minus 3. Divide both sides by 100, you get 1/4 equals r squared. And you take the square root of both sides, r is equal to 1/2. So your explicit formula is a sub n equals 100 times 1/2 to the n minus 3. That's our explicit formula. And then to find the 13th term, we're going to plug in 13 for n. Just be very careful on the calculator and their order of operations. I did it again, 13 minus 3, not 10. And if you do that out in the calculator and you round to 3 decimals, you get 0.098. Okay, so that's it for geometric. I realized might have been a little bit long, but hopefully it gives you a good sense of all this sequences. Luckily, that's the last sequence we're going to learn. We're going to learn ways to sum up sequences a little bit later, but in terms of creating sequences, it's arithmetic and geometric, and you guys are done at that point, okay? So your homework tonight is to do worksheet number 7. I realize we skipped number 5. Don't worry about that. Yeah, try worksheet 7. Why don't you actually do one problem? Why don't you do the odds from each section? So 1, 3, 5, and 7. So homework, just to write this out. Oops. Homework. Okay. 1, 3, 5, and 7 from worksheet number 7.